63 light-years away from Earth, floating in the darkness of space, there exists a planet that looks like paradise from a distance. If you could see it with your own eyes from a spacecraft approaching the system, you would witness a gorgeous cobalt blue marble suspended against the black void, visually similar to our own precious Earth. The color is striking, mesmerizing, almost inviting. But this resemblance is the most deceptive lie in the known universe. If you could somehow survive on this world for even 1 second, you would experience a death more violent than anything conceived in science fiction. This is HD 189733b, and it is a vision of hell wrapped in the appearance of heaven. The planet is slightly larger than Jupiter, a gas giant with no solid surface to speak of, swirling with atmospheric chaos that makes Jupiter's great red spot look like a gentle breeze. But the truly alien aspect of this world is its orbital period. HD 189733b completes 1 full orbit around its parent star in just 2.2 days. Think about that for a moment. A year on this planet lasts barely longer than a weekend on Earth. This is because the planet orbits so close to its star that it exists in a state of tidal locking, with one side perpetually facing the blazing stellar furnace, while the other side remains trapped in eternal darkness. The same hemisphere always faces the star, just as the same side of our moon always faces Earth, except the consequences here are infinitely more extreme. This bizarre world first entered human awareness in 2005 when the Hubble Space Telescope detected it during one of humanity's early surveys of exoplanets. Astronomers were immediately excited by what they saw. The initial observations suggested a planet with an Earth-like blue color, and for a brief moment, the scientific community buzzed with speculation. Could this be a world with water? Could this be another Earth-like planet? The excitement was palpable. The possibilities seemed endless. But then came 2007, a year that would forever change our understanding of this distant world. The Spitzer Space Telescope, with its infrared capabilities, created the first-ever temperature map of an exoplanet's atmosphere. And what it revealed was nothing short of shocking. This was no paradise. This was a nightmare world where temperatures soared to levels that would instantly vaporize any spacecraft humanity could build. The hellish truth had been revealed, and it was far more terrifying than anyone had imagined. The discovery of HD 189733b represents one of the landmark moments in exoplanet science, not just because of what we found, but because of how we found it. Astronomers detected this planet using what's called the transit method, one of the most productive techniques we have for finding worlds orbiting distant stars. The principle is elegant in its simplicity. When a planet passes in front of its star from our perspective here on Earth, it blocks a tiny fraction of the star's light. By carefully measuring the brightness of the star over time, astronomers can detect these tiny dips in luminosity, revealing the presence of an orbiting world. HD 189733b was particularly easy to spot because of its size and proximity to its star. Being larger than Jupiter and orbiting so close to its parent star meant that it blocked a significant amount of light during each transit, creating a clear signal that was impossible to miss. But detecting the planet was just the beginning. The real breakthrough came when scientists began analyzing the light that passed through the planet's atmosphere during these transits. This technique, called transmission spectroscopy, allows us to determine the chemical composition of a distant planet's atmosphere by examining how different wavelengths of light are absorbed or scattered. When the first spectroscopic readings came back from HD 189733b, scientists were puzzled. The atmospheric signature didn't match anything they had expected. There were absorption features that suggested the presence of certain molecules, but the overall pattern was strange, almost contradictory. The blue color remained a mystery. On Earth, our planet appears blue from space primarily because of our vast oceans, which cover more than 70% of the surface. Water absorbs red light and reflects blue light, creating the characteristic color we all recognize from satellite imagery. Scientists initially wondered if HD 189733b might have a similar explanation. Perhaps this gas giant had water vapor in its upper atmosphere, creating a blue haze. But the spectroscopic data didn't support this hypothesis. The chemical signatures weren't quite right for water vapor in the concentrations needed to produce such a deep blue color. Then came the moment of realization, one of those pivotal points in science where the puzzle pieces suddenly click together. Researchers began to suspect that the blue color wasn't from water at all, but from something far more sinister. The hypothesis that emerged was almost too bizarre to believe. What if the atmosphere contained silicate particles? Silicates are the primary components of rocks and sand on Earth, the minerals that make up most of our planet's crust. On Earth, these materials are solid, locked in planetary geology. But on HD 189733b, with its extreme temperatures, these rocky materials could exist in vaporized or particulate form, suspended in the atmosphere. In 2013, the Hubble Space Telescope conducted a detailed observation campaign that would confirm this shocking hypothesis. Using its advanced spectroscopic instruments, Hubble definitively detected the presence of silicate particles scattered throughout HD 1897b's atmosphere. The blue color that had initially excited astronomers wasn't from water creating a paradise world. It was from clouds of vaporized glass and rocky material creating an atmospheric nightmare. This discovery transformed HD 1897 from an interesting exoplanet into one of the most intensely studied worlds beyond our solar system. Over the following years, more than 50 scientific papers would be published analyzing various aspects of this planet's properties, each one revealing new details about the extreme conditions that exist there. The science behind HD 189733b's distinctive cobalt blue color is both fascinating and terrifying. To understand why this planet appears the way it does, we need to dive into the physics of light scattering and atmospheric optics. When light from the planet's star strikes the atmosphere, it encounters countless tiny particles suspended in the gas. These particles are composed primarily of magnesium silicate, the same basic material found in Earth's rocks, sand, and glass. But here's where things get interesting. The size of these particles determines exactly how they interact with light. Particles that are roughly the same size as the wavelength of blue light, around 450 nanometers, are particularly effective at scattering blue wavelengths while allowing red wavelengths to pass through relatively unimpeded. This is similar to what happens in Earth's atmosphere through a process called Rayleigh scattering. On Earth, molecules of nitrogen and oxygen scatter blue light from the sun in all directions, which is why we see a blue sky during the day. But Earth's atmospheric scattering creates a pale, relatively light blue, nothing like the deep, rich cobalt color of HD 189733b. The difference lies in the particles doing the scattering. On HD 189733b, the silicate particles are larger and more numerous than the molecules in Earth's atmosphere. They create what scientists call Maie scattering, which is more efficient at scattering light and can produce more intense colors. The specific wavelengths that are absorbed and reflected by the silicate particles create that distinctive deep blue hue. Red and green wavelengths are partially absorbed by the particles, while blue wavelengths are scattered intensely, creating the stunning color we observe. Different particle sizes would create different shades of blue, and scientists can actually use the precise shade they observe to make inferences about the size distribution of particles in the atmosphere. Some particles might be microscopic, just a few microns across, while others could be significantly larger, approaching the size of sand grains. This variation in particle size creates a complex scattering environment that produces the specific shade of cobalt blue that makes HD 1897 so visually distinctive. In fact, this planet's blue color is so characteristic that astronomers could potentially identify it from incredible distances, even without detailed spectroscopy. If future generations of telescopes were to take actual images of this planet, rather than just detecting it through transits, that blue color would be immediately recognizable. A cosmic signature unlike anything else we've discovered. The irony is profound and unsettling. The color that makes this planet beautiful is produced by the very material that makes it deadly. Now we must transition from the beautiful imagery of this distant blue world to the horrific reality of what actually exists there. HD 189733 may look serene from a distance, but up close, it is a realm of unimaginable violence and chaos. There are three primary features that make this planet one of the most hostile environments ever discovered. Three interlocking nightmares that work together to create conditions that would destroy anything we could send there. First, there are the temperatures, which reach levels that would instantly vaporize most materials known to science. Second, there are the winds, which scream through the atmosphere at speeds that defy comprehension, carrying everything in their path at velocities that make Earth's most powerful hurricanes look gentle by comparison. Third, there is the rain, except this rain isn't made of water. It's made of glass, composed of the same silicate particles that give the planet its blue color, and these glass particles are carried horizontally by those hypersonic winds, creating a perpetual sandblasting effect that could shred any material in seconds. Throughout human history, we have been fascinated by extreme environments. Ancient civilizations told stories of underworlds filled with fire and brimstone, of frozen wastelands at the edges of the world, of places where the gods themselves would not venture. Medieval scholars speculated about the nature of other celestial bodies, wondering if the moon or the planets might harbor regions of extreme heat or cold. As our scientific understanding grew, we discovered extreme environments on our own planet. The crushing pressures of the deepest ocean trenches, where the weight of water above would instantly compress any human body. The searing heat of volcanic vents, where temperatures exceed the melting point of lead. The frozen deserts of Antarctica, where winter temperatures drop below -100 degrees Fahrenheit. The acidic lakes of volcanic calderas, where water is so chemically hostile that almost nothing can survive. These Earth-based extremes became our baseline for understanding what hostile environments could be like. But HD 189733b makes all of them look comfortable by comparison. The most extreme place on Earth is a 5-star resort compared to the conditions on this planet. To truly grasp the horror of HD 189733b, we need to understand just how much worse than Earth's extremes this place really is. The deepest point in Earth's oceans experiences pressures of about 1,000 atmospheres. The pressures on HD 189733b reach levels thousands of times higher as you descend through the gas giant's atmosphere. The hottest natural temperature ever recorded on Earth's surface is about 134 degrees Fahrenheit, measured in Death Valley. The average temperature on HD 189733b's day side is around 1,800 degrees Fahrenheit, more than 13 times hotter. The fastest wind speed ever recorded on Earth was 253 miles per hour during Tropical Cyclone Olivia in 1996. The winds on HD 189733b reach 5,400 miles per hour, more than 20 times faster. These aren't just quantitative differences. They represent qualitatively different regimes of physics, conditions so extreme that materials behave in ways we rarely encounter in everyday life. To understand HD 189733b's extremes, we first need to understand what category of planet it represents. In the classification scheme that astronomers have developed for exoplanets, HD 189733b belongs to a class called hot Jupiters. These are gas giant planets similar in size and composition to our own Jupiter, but with one crucial difference. They orbit extremely close to their parent stars, much closer than Mercury orbits our Sun. The term hot Jupiter was coined in the mid-1990s, when the first exoplanets were discovered orbiting Sun-like stars. Before these discoveries, most scientists assumed that planetary systems would resemble our own solar system, with small rocky planets close to the star and large gas giants farther out. This assumption made sense based on planet formation theory. Gas giants form in the outer regions of planetary systems where it's cold enough for volatile compounds like water and methane to condense into ice, providing the solid material needed to build a large planetary core that can then attract and hold on to massive amounts of hydrogen and helium gas. But the universe, as it so often does, surprised us. The first exoplanets discovered around Sun-like stars were hot Jupiters, massive worlds orbiting closer to their stars than Venus orbits the Sun. This discovery forced a revolution in our understanding of how planetary systems form and evolve. We now know that gas giants can migrate inward from their formation locations, moving through the protoplanetary disk and settling into close orbits around their stars. This migration process likely involves complex gravitational interactions with the disk material and with other planets in the system. Hot Jupiters are, in some ways, easier to detect than other types of exoplanets. Their large size means they block more light during transits, creating bigger, easier-to-measure signals. Their close orbits mean they transit frequently, giving astronomers multiple opportunities to observe them in a relatively short time period. As a result, hot Jupiters were among the first exoplanets to be discovered and characterized in detail. But within the hot Jupiter category, there is tremendous diversity. Some are merely hot, with temperatures of a few hundred degrees. Others, like HD 189733b, are extremely hot, with temperatures that can vaporize rock. Some have relatively calm atmospheres, while others have the most violent weather patterns ever observed. HD 189733b is considered typical in some ways. Its size is average for a hot Jupiter. Its orbital period of 2.2 days is common for this class of planet. Its tidal locking is expected given its proximity to its star, but in other ways, HD 189733b represents an extreme even among hot Jupiters. The wind speeds measured on this planet are among the highest ever detected on any exoplanet. The conformation of silicate clouds makes it stand out as particularly exotic. The atmospheric loss rate is remarkable, even for a hot Jupiter being bombarded by stellar radiation. To put HD 189733b's orbital distance in perspective, consider this. Earth orbits the Sun at an average distance of 93 million miles, a distance that astronomers call 1 astronomical unit. Mercury, the closest planet to the Sun in our solar system, orbits at a distance of about 36 million miles, or 0.4 astronomical units. HD 189733b orbits its star at a distance of just 3 million miles, or roughly 0.03 astronomical units. That's 12 times closer than Mercury, 30 times closer than Earth. At this distance, the gravitational influence of the star is immense, creating the tidal locking that keeps one face of the planet perpetually roasting under stellar radiation while the other face remains in darkness. This proximity also means that the planet receives an enormous amount of energy from its star, energy that drives the extreme temperatures and violent atmospheric dynamics we observe. But HD 18973 is far from the only nightmare world in the universe. As our exoplanet surveys have continued and our instruments have grown more sophisticated, we've discovered dozens of other planets with conditions that challenge our imagination and our understanding of planetary physics. Some planets are even hotter than HD 189733b, with atmospheres where metals vaporize. Some have stranger atmospheric compositions, with clouds made of materials we'd consider exotic or impossible on Earth. Some have even more extreme wind patterns or temperature differentials. Throughout this exploration, we'll encounter several of these nightmare worlds, each one revealing a different aspect of just how hostile planets can be. But HD 189733 remains special. A blue jewel of death that looks like paradise but represents a form of hell that would make Earth's worst nightmares seem tame. This is where our journey truly begins, into the heart of the temperature inferno that defines this world. The day side of HD 189733b exists in a state of perpetual thermal assault. The temperature on the hemisphere that permanently faces the star reaches approximately 1800 degrees Fahrenheit, or 980 degrees Celsius. To truly grasp what this means, we need to understand that this isn't just hot in the way we experience heat on Earth. This is hot enough to fundamentally alter the state of matter itself. At 1800 degrees Fahrenheit, aluminum would be a puddle of liquid metal, having long since exceeded its melting point of 1221 degrees. Silver would be molten, its melting point of 1763 degrees comfortably exceeded. Lead, zinc, and numerous other metals would have vaporized entirely, transformed from solid metal into gaseous atoms floating in the atmosphere. Even gold, that noble metal prized throughout human history for its durability and resistance to corrosion, would be approaching its melting point of 1948 degrees Fahrenheit. On HD 189733b's day side, you could potentially encounter clouds of liquid gold droplets suspended in the atmosphere, a sight that would be beautiful if it weren't so utterly deadly. The source of this infernal heat is obvious, yet staggering in its implications. The star that HD 189733b orbits is slightly smaller and cooler than our Sun, classified as a K-type star. But the planet orbits so close that it receives hundreds of times more radiation per square meter than Earth receives from the Sun. Imagine standing under the midday sun on the hottest day of summer, feeling the heat on your skin, the warmth that can cause sunburn after prolonged exposure. Now multiply that intensity by several hundred times. The stellar radiation bombarding HD 189733b's dayside isn't just visible light and warmth. It's a full-spectrum assault of electromagnetic energy, including intense ultraviolet radiation and X-rays that would shred molecular bonds and ionize atoms on contact. This radiation doesn't just heat the surface, because there is no surface in the way we understand it. HD 189733b is a gas giant, similar in composition to Jupiter, meaning it has no solid ground to stand on. If you could somehow survive long enough to descend into the planet, you would find that the atmosphere gradually transitions from gas to liquid to exotic states of matter under increasing pressure and temperature. But there's no definitive boundary where you could say the atmosphere ends and the planet begins. The entire structure is a continuous gradient of density and pressure, getting more extreme the deeper you go. At the temperature of the day side, many compounds that we consider stable simply cannot exist in their normal forms. Water, if it were present, would be superheated steam at these temperatures and pressures. But spectroscopic observations suggest very little water vapor in the upper atmosphere that we can observe. Methane, ammonia, and other compounds common on cooler gas giants exist only in broken, ionized forms, if at all in the dayside inferno. The chemistry occurring at these temperatures is exotic, dominated by highly reactive atomic and ionic species, rather than the stable molecules we're familiar with. The dayside represents a regime of constant thermal violence, where the fundamental processes of chemistry and physics operate in ways we rarely encounter in laboratory conditions on Earth. The night side of HD 189733b tells a very different story, though one that's still fundamentally alien by Earth standards. The hemisphere, trapped in permanent darkness, experiences temperatures that drop to around 1200 degrees Fahrenheit. Read that number again. 1200 degrees. This is the cool side of the planet. To put this in perspective, 1200 degrees Fahrenheit is still hot enough to melt aluminum with ease. It's hotter than the melting point of most common metals. It's approximately the temperature of molten lava emerging from volcanic vents on Earth. On our planet, 1200 degrees would represent an extreme temperature found only in the most violent geological processes or in industrial furnaces. On HD 189733, this is what passes for cool. The temperature differential between day and night sides is approximately 600 degrees Fahrenheit, and this gradient is remarkable for several reasons. In most planetary atmospheres, heat tends to redistribute relatively efficiently. On Earth, our atmosphere and oceans work together to transport heat from the equator toward the poles, moderating temperature differences and creating relatively uniform conditions around the globe. Even on other planets in our solar system with less efficient heat transport, temperature differentials are usually much smaller than we see on HD 189973b. Venus, despite its incredibly dense atmosphere and extreme greenhouse effect, has almost no temperature difference between its day and night sides because the thick atmosphere redistributes heat so effectively. Jupiter and Saturn, our local gas giants, have internal heat sources that supplement solar heating and create relatively uniform temperatures at similar atmospheric pressures. But HD 189733b maintains this dramatic 600-degree differential, suggesting that heat transport between the day and night sides is surprisingly inefficient, despite the powerful winds we'll discuss later. The permanent darkness of the night side creates an environment unlike anything else in the observed universe. Imagine standing on that night side if you could somehow survive the heat and pressure. You would see no sun, no stars, nothing but absolute blackness in the sky above. The only illumination would come from the thermal glow of the atmosphere itself, a dim red or orange radiance from the surrounding heat, perhaps punctuated by lightning if electrical storms exist in these conditions. The darkness is not just an absence of light, but a fundamental feature of the planet's existence. For billions of years, this hemisphere has existed in shadow, never once seeing the light of its star, locked in eternal night by the same gravitational forces that keep one face of our moon always pointed toward Earth. In this darkness, exotic chemistry unfolds. The temperature transition zone between the blazing day side and the relatively cooler night side creates conditions where materials undergo dramatic phase changes. Compounds that exist as vapor on the day side condense into liquid droplets or even solid particles as they are carried by atmospheric winds toward the cooler night side. This process is similar to how water vapor in Earth's atmosphere condenses into clouds and precipitation, except here the materials condensing are things like silicates, metals, and other refractory compounds that we think of as rocks and ores on Earth. The night-side atmosphere likely contains clouds of these condensed materials, creating an environment that would be utterly opaque to visible light even if there were a light source to illuminate it. The chemistry in the transition zone is dominated by condensation reactions, where gaseous atoms and molecules combine into larger structures, releasing energy in the process. But despite this exotic chemistry and the powerful winds carrying heat from day to night, the temperature differential persists, suggesting that the mechanisms of heat transport on HD 18973b are not as efficient as we might expect. The boundary between day and night on HD 18973b is called the terminator zone, and it's here that the planet's most violent weather phenomena occur. The terminator is not a thin line, but rather a broad transitional region where the eternal day fades into eternal night, where temperatures plummet by hundreds of degrees over relatively short distances, and where the atmospheric dynamics reach their most chaotic extremes. Imagine crossing from the day side to the night side. As you move away from the subsolar point, the point on the planet's surface directly beneath the star, temperatures begin to drop. At first, the change is gradual, but as you approach the terminator zone, the temperature gradient steepens dramatically. You would experience a temperature shock unlike anything possible on Earth, moving from 1800 degrees to 1200 degrees over a distance that might span only a few hundred miles on the planet's surface. This creates enormous thermal gradients that drive powerful atmospheric circulation. Hot gas rises on the day side, flows toward the night side at high altitudes, descends on the night side, and returns to the day side at lower altitudes, completing a massive convection cycle. But this simple description doesn't capture the complexity and violence of what actually occurs. The terminator zone is where materials undergo dramatic phase changes. Compounds that exist as gases on the day side begin to condense as temperatures drop. Silicate particles, which we'll discuss in detail later, form clouds as vaporized rock cools and solidifies. Potentially, metal vapors condense into liquid droplets. The atmosphere becomes a laboratory for exotic precipitation processes, where materials we think of as solid rocks or metals cycle between gas, liquid, and solid phases driven by the temperature differential. Scientific observations of HD 18973 have revealed asymmetric heating, patterns that confirm the complexity of the terminator zone. When the Spitzer Space Telescope created its thermal map of the planet, it showed that the hottest point on the planet is not directly under the star as you might expect, but is offset by several degrees to the east, in the direction of the planet's rotation. This offset suggests that atmospheric winds carry hot material away from the subsolar point before it can cool and descend, creating a complex temperature distribution that doesn't simply mirror the pattern of stellar heating. The terminator zone is also where the most extreme wind patterns emerge. The temperature gradient creates pressure differences that drive powerful winds, which we'll explore in detail in the next section. But it's worth noting here that the transition from day to night is not a calm, gradual process, but rather a violent, turbulent region where atmospheric dynamics operate at their most extreme. If you could observe the terminator zone from above, you would see swirling patterns of clouds and haze, convective towers rising from the hot day side and collapsing on the cool night side. Perhaps lightning flickering through the clouds as electrical charges separate in the turbulent atmosphere. The terminator zone represents a boundary not just between light and dark, but between different physical regimes, different chemical environments, different states of matter. It's a region where the planet's fundamental nature as a world of extremes is most clearly on display. To understand why HD 189733b has such extreme and permanent temperature differentials, we need to understand the phenomenon of tidal locking. Tidal locking occurs when an object's orbital period matches its rotational period, meaning it completes one rotation on its axis in exactly the same time it takes to complete one orbit around its parent body. The result is that the same face of the object always points toward the thing it's orbiting. You're already familiar with the most prominent example of tidal locking in our solar system, our own moon. The moon is tidally locked to Earth, which is why we always see the same face of the moon from Earth's surface. The so-called dark side of the moon, more accurately called the far side, never faces Earth and remained completely unknown to humanity until spacecraft could photograph it from orbit. But the moon took billions of years to become tidally locked to Earth. The process is driven by tidal forces, the differential gravitational pull that the Earth exerts on the near and far sides of the moon. These forces create bulges in the moon's shape, and, as the moon initially rotated at a different rate than its orbital period, these bulges moved around the moon, creating internal friction that dissipated energy and gradually slowed the moon's rotation until it matched the orbital period. For HD 189733, tidal locking happened much more quickly, probably within just a few million years of the planet's formation. The reason is the extreme proximity to its star. Remember, this planet orbits at just 3 million miles, 30 times closer than Earth orbits the Sun, and 12 times closer than Mercury. At this distance, the tidal forces exerted by the star on the planet are enormous, far greater than the tidal forces between Earth and Moon. The star's gravity pulls more strongly on the side of HD 189733b facing it than on the far side, creating massive tidal bulges. As the planet initially rotated, these bulges moved around the planet, creating internal friction that rapidly dissipated the planet's rotational energy. Within a cosmically short time, the planet's rotation slowed to match its orbital period, and it became tidally locked. This process is essentially inevitable for planets orbiting this close to their stars. Every hot Jupiter we've studied shows evidence of tidal locking. The gravitational forces involved are simply too powerful for the planet to maintain an independent rotation over astronomical timescales. But why does tidal locking create such extreme temperature differentials? The answer lies in the fact that one side of the planet receives constant, unrelenting stellar radiation, while the other side receives none. On Earth, our 24-hour rotation period ensures that every point on the surface experiences day and night, heating and cooling in a daily cycle that prevents any location from getting too hot or too cold. Our atmosphere and oceans have time to redistribute heat, and no region becomes thermally isolated from the rest of the planet. But on a tidally locked planet like HD 189733b, there is no day-night cycle. The day side has been baking under stellar radiation for billions of years without interruption. The night side has been in darkness for the same amount of time, never receiving direct heating from the star. This creates a fundamental asymmetry that no amount of atmospheric circulation can completely overcome. Heat must be constantly transported from day to night to prevent even more extreme temperature differences, but the transport is never fully efficient, resulting in the 600-degree differential we observe. Beyond the extreme temperatures, HD 189733 presents another nightmare: atmospheric pressure that would crush any object we could conceive of sending there. As a gas giant, the planet has no solid surface, but rather a continuous atmosphere that gets progressively denser as you descend deeper into the planet. At the top of the atmosphere, where space transitions into planetary environment, the pressure is relatively low, perhaps comparable to Earth's atmosphere. But descend just a short distance, and the pressure begins to climb rapidly. At the altitude where we can observe the planet using spectroscopy, detecting the chemical signatures of atmospheric constituents, the pressure is already many times greater than Earth's surface pressure. Continue descending, and the pressure increases exponentially. Within the first few hundred miles, you would encounter pressures hundreds or thousands of times greater than Earth's atmosphere. At a depth of perhaps 1,000 miles, pressures would reach levels where the very nature of matter begins to change. The hydrogen that makes up the bulk of the planet's mass would be compressed so thoroughly that it stops behaving like a normal gas. Deeper still, pressures reach millions of times Earth's atmospheric pressure, and hydrogen transitions into a state called metallic hydrogen. In this exotic phase, hydrogen atoms are squeezed so close together that their electrons break free and move throughout the material, conducting electricity like a metal. This metallic hydrogen layer likely exists throughout a large portion of HD 189733b's interior, creating a vast ocean of liquid metallic hydrogen surrounding whatever core might exist at the planet's center. The core itself is a mystery. It might be a dense ball of rock and ice, the primordial seed around which the gas giant formed, compressed to unimaginable densities by the weight of the planet above it. Or the core might have dissolved into the surrounding metallic hydrogen over billions of years, its material distributed throughout the deep interior. To understand just how extreme these pressures are, consider what happens in Earth's deepest oceans. The Mariana Trench, the deepest point in Earth's oceans, reaches a depth of about 7 miles below sea level. At the bottom of the trench, the pressure is approximately 1,000 times Earth's atmospheric pressure, enough to crush most submarines unless they're specifically designed with thick titanium or steel hulls to resist the compression. A human body exposed to these pressures would be crushed instantly, every airspace compressed, every bone shattered by the immense force of water pushing from all directions. The pressure would force water into every tissue, every cell, destroying biological structure completely. This is among the most extreme pressures found naturally on Earth's surface, and it represents the absolute limit of where humans can send robotic explorers without extraordinary engineering. On HD 189733b, these pressures are encountered just a short distance into the atmosphere, and they're merely the beginning. Descend deeper, and pressures climb to levels that make the bottom of the Mariana Trench look like a gentle environment. At depths of a few thousand miles, pressures exceed 1,000,000 times Earth's atmosphere. No material known to science could maintain its structure under these conditions. Diamond, the hardest naturally occurring material on Earth, would be compressed and deformed. Steel would flow like liquid. Any spacecraft attempting to descend would be crushed long before reaching these depths, compressed into a ball of increasingly dense material as the pressure overwhelmed every structural element. But even these extreme pressures pale in comparison to what exists in the deepest interior of HD 18973b. Near the core, pressures might reach tens of millions of times Earth's atmospheric pressure. Conditions so extreme that matter behaves in ways we can only study theoretically or in the most sophisticated laboratory experiments. The entire planet is a pressure gradient from merely extreme at the top to inconceivably extreme at the center, and every layer represents conditions that would instantly destroy anything we could build with current technology, or even with technology we can currently imagine. In 2015, a team of astronomers from the University of Warwick published a study that would fundamentally change our understanding of extreme planetary weather. Using sophisticated spectroscopic analysis of HD 18973b, they measured wind speeds in the planet's atmosphere that seemed almost impossible to believe. The winds on this planet reach velocities of 5,400 miles per hour. Read that number again and let it sink in. 5,400 miles per hour. To put this in perspective, this is approximately 7 times the speed of sound in Earth's atmosphere. These are not merely supersonic winds. They are hypersonic winds, moving so fast that they create physical conditions unlike anything we experience on our planet. The measurement itself represents a triumph of modern astronomical technique. Scientists cannot directly observe the winds on HD 18973b. The planet is too far away, too small, and too close to its bright parent star for us to see surface features or cloud movements the way we can observe weather patterns on Jupiter or Saturn through telescopes. Instead, researchers used a technique called Doppler spectroscopy, the same basic principle that police use in radar guns to measure the speed of cars on highways. When light comes from an object moving toward you, its wavelength gets compressed, shifting toward the blue end of the spectrum. When light comes from an object moving away from you, its wavelength gets stretched, shifting toward the red end of the spectrum. By carefully analyzing the light coming from different parts of HD 18973b's atmosphere during a transit when the planet passes in front of its star, astronomers could measure how much the light was shifted by the motion of atmospheric gases. One side of the planet shows a blue shift, where gases are moving toward us. The other side shows a red shift, where gases are moving away from us. The magnitude of these shifts reveals the velocity of the winds carrying atmospheric material around the planet. When the University of Warwick team completed their analysis, the numbers were staggering. To understand just how fast 5,400 miles per hour really is, we need some comparisons to familiar speeds. The fastest winds regularly encountered on Earth are jet streams, rivers of air flowing at high altitudes where weather systems and commercial aircraft travel. Jet streams typically move at speeds of around 200 miles per hour, fast enough to significantly affect flight times for aircraft traveling with or against these currents. The fastest tornado winds ever recorded reached approximately 300 miles per hour, creating the devastating EF5 tornadoes that can level entire communities. These represent the most violent atmospheric phenomena on Earth, winds so powerful that they can drive pieces of straw through tree trunks and hurl cars hundreds of yards. But even these extreme winds are gentle compared to what exists on HD 189733b. To find winds that come anywhere close, we have to look beyond Earth to other planets in our solar system. Neptune, the outermost ice giant, holds the record for the fastest winds in our solar system at approximately 1,200 miles per hour. These supersonic winds race through Neptune's upper atmosphere, driven by the planet's internal heat and rapid rotation. For decades, Neptune's winds represented the most extreme atmospheric velocities known to science. HD 189733b's winds are more than 4 times faster. At 5,400 miles per hour, you could cross the entire continental United States in approximately 30 minutes. You could circle the entire Earth in about 5 hours. These aren't just fast winds. They represent velocities normally associated with spacecraft in orbital flight, not atmospheric phenomena. What drives winds to such extreme velocities? The answer lies in the fundamental physics of atmospheric dynamics combined with the extreme conditions on HD 18733b. All winds, whether on Earth or on distant exoplanets, are driven by temperature and pressure differences. Hot air rises, creating areas of low pressure. Cool air sinks, creating areas of high pressure. Air flows from high pressure to low pressure, and this flow is what we experience as wind. The greater the temperature difference, the greater the pressure difference, and the stronger the winds. On HD 189733b, the temperature difference between the day side and night side is approximately 600 degrees Fahrenheit, a gradient that would be absolutely impossible on Earth. This creates pressure differences on a scale we never encounter in our atmosphere. Hot gas on the day side expands and rises, creating a massive, low-pressure region. Cooler gas on the night side contracts and sinks, creating a high-pressure region. The atmosphere wants to flow from the high-pressure night side to the low-pressure day side to equalize these differences, but the planet's rotation, however slow, deflects this flow, creating the high-speed winds we observe. But there's something even more remarkable happening on HD 189733b beyond simple pressure-driven winds. The planet exhibits what atmospheric scientists call superrotation, a phenomenon where the atmosphere moves faster than the planet itself rotates. Remember, HD 189733b is tidally locked, completing one rotation every 2.2 days to match its orbital period. This is an incredibly slow rotation by planetary standards. Earth completes one rotation every 24 hours. Jupiter rotates once every 10 hours, despite being vastly larger. But HD 189733b's atmosphere doesn't just rotate once every 2.2 days. It races around the planet much faster, completing a full circuit in a fraction of that time. The winds, measured at 5,400 miles per hour, are moving far faster than the surface of the planet is rotating. This superrotation is driven by the absorption of stellar radiation and the subsequent heating patterns in the atmosphere. Hot gas rises on the day side and flows toward the night side at high altitudes. But rather than flowing in a simple pattern from day to night, the moving air is influenced by something called the Coriolis effect. On Earth, the Coriolis effect is caused by our planet's rotation and is responsible for the curved paths of hurricanes and the general circulation patterns in our atmosphere. Objects moving across a rotating surface appear to curve because the surface beneath them is rotating at different speeds at different latitudes. On HD 189733b, despite the slow rotation of the planet itself, The massive temperature gradients and the resulting pressure differences create Coriolis-like effects that deflect the flowing air, causing it to circulate around the planet rather than simply flowing directly from day side to night side. The result is a powerful eastward flow, winds that blow from west to east, carrying enormous amounts of heat from the day side around to the night side. This is why the hottest point on the planet is not directly under the star, but is offset to the east. The winds have carried hot material away from the subsolar point before it can cool and descend. This circulation pattern represents one of the most efficient heat transport mechanisms ever observed on a planet. Yet, even this incredible wind system cannot fully equilibrate the day-night temperature difference, which remains at 600 degrees. The atmospheric circulation on HD 18973b is dominated by a single planet-wide jet stream, and this structure makes the planet's weather patterns fundamentally different from what we see on Earth or even on other planets in our solar system. On Earth, we have multiple jet streams at different latitudes. The polar jet streams flow around the Arctic and Antarctic regions at latitudes of about 60 degrees. The subtropical jet streams flow at around 30 degrees latitude. These jet streams are separated by regions of slower winds, and they meander north and south, creating the complex weather patterns we experience. The jet streams on Earth rarely exceed 200 miles per hour and occur at altitudes of around 30,000 to 40,000 feet, right around the cruising altitude of commercial aircraft. Jupiter and Saturn, our local gas giants, have multiple jet streams arranged in bands at different latitudes. Jupiter has about 12 distinct jet streams alternating between eastward and westward flows. These create the visible banded structure we see when we look at Jupiter through a telescope, light-colored zones alternating with dark-colored belts. The winds in these jets can reach speeds of up to 400 miles per hour. Impressive by Earth standards, but modest compared to HD 189733b. The Great Red Spot, Jupiter's famous storm system, sits at the boundary between two of these jet streams where the wind shear creates turbulent conditions conducive to long-lived vortices. Saturn has a similar banded structure with multiple jets, including a bizarre hexagonal jet stream around its north pole, a geometric pattern that emerges from the complex fluid dynamics in Saturn's atmosphere. But HD 189733b is different. Instead of multiple jets at different latitudes, the planet has a single dominant jet stream that encircles the entire planet near the equator. This equatorial jet carries the 5,400 mile per hour winds that transport heat from the day side to the night side. The jet occurs at high altitudes in the atmosphere, in regions where the pressure has dropped to levels that are merely crushing, rather than incomprehensibly extreme, though still far higher than anything on Earth. Within this jet stream, conditions are chaotic. The temperature gradients, the extreme velocities, and the turbulent mixing all combine to create an atmospheric environment of incredible violence. Turbulence within the jet would be experienced as constant, extreme buffeting, with wind speeds varying by hundreds of miles per hour over short distances or short time periods. Any object caught in this jet stream would be subject to forces that would tear apart anything we could construct. Why does HD 189733b have this simple structure of a single equatorial jet rather than the multiple jets we see on Jupiter and Saturn? The answer lies in the tidal locking and the resulting temperature distribution. On Jupiter and Saturn, the heating from the Sun is relatively uniform around the planet because these planets rotate rapidly, exposing all longitudes to sunlight in quick succession. The temperature differences that drive jet streams are primarily between different latitudes, between the equator and the poles, leading to multiple jets at different latitudes. On HD 189733b, the primary temperature difference is not between equator and poles, but between the day side and night side. This creates a fundamentally different circulation pattern, dominated by the flow of heat around the planet from day to night, which naturally concentrates into a single powerful equatorial jet, rather than splitting into multiple jets at different latitudes. When an object moves through air faster than the speed of sound, something remarkable and violent happens. Sound waves are pressure waves that propagate through air at a finite speed, approximately 767 miles per hour at sea level on Earth. When an object moves slower than the speed of sound, it continuously generates pressure waves that propagate ahead of it, essentially announcing the object's approach to the air molecules in front of it. But when an object exceeds the speed of sound, it outruns its own pressure waves. The air in front of the object has no warning that something is approaching. The result is a shock wave, a discontinuous jump in pressure, temperature, and density that we experience as a sonic boom. Fighter jets exceeding the speed of sound create sonic booms that rattle windows and can be heard for miles. The space shuttle re-entering Earth's atmosphere created double sonic booms from its nose and tail that announced its return to those on the ground. But these are discrete events, individual objects passing through the air at supersonic speeds. On HD 189733b, the entire atmosphere is moving at supersonic speeds continuously, creating a permanent state of sonic violence. At 5,400 miles per hour, the winds are approximately 7 times the speed of sound, well into the hypersonic regime. At these velocities, the physics of airflow becomes dramatically more extreme. The air molecules literally cannot get out of the way fast enough. They slam into each other with enormous force, creating shock waves that propagate through the atmosphere. But these are not simple sonic booms. At hypersonic speeds, the shock waves become incredibly strong, and the compression of air within these shock waves generates tremendous heat. This is called compression heating, and it's the same phenomenon that causes spacecraft to glow red hot during atmospheric re-entry. When the Apollo capsules returned from the Moon, they hit Earth's atmosphere at approximately 25,000 miles per hour. The compression heating from this hypersonic entry was so intense that the heat shield protecting the astronauts reached temperatures of around 5,000 degrees Fahrenheit, hot enough to vaporize most materials. The heat shield was made of a special ablative material designed to slowly burn away, carrying heat with it and protecting the astronauts inside. On HD 189733b, compression heating is occurring throughout the atmosphere continuously. The hypersonic winds slamming into relatively stationary air masses create shock waves that heat the gas even further, adding to the already extreme temperatures from stellar radiation. The atmosphere itself becomes a weapon. Any solid object in these wind streams would be subjected to shock waves that would shatter molecular bonds and vaporize material. The compression waves wouldn't just push on an object, they would fundamentally alter its structure at the molecular level. Humanity has spent decades developing hypersonic weapons, missiles, and aircraft that can fly at speeds exceeding 5 times the speed of sound. These weapons are difficult to develop because materials must withstand the extreme heating and pressure of hypersonic flight. Leading edges of hypersonic vehicles can reach temperatures exceeding 3,000 degrees Fahrenheit just from compression heating. Special materials and cooling systems are needed to prevent the vehicle from melting or disintegrating. engineers must carefully design the shape of hypersonic vehicles to manage shock waves and minimize heating. On HD 189733b, nature creates hypersonic conditions continuously throughout the entire atmosphere, at velocities that exceed our most advanced hypersonic technology. The planet represents a natural laboratory for hypersonic physics operating at scales and intensities that we cannot replicate in laboratory conditions or even in weapons tests. The continuous sonic violence of this atmosphere makes it utterly hostile to any form of intrusion. There is no material that could survive in these wind streams for more than a fraction of a second before being heated, compressed, and ultimately vaporized by the hypersonic environment. Beyond the already extreme conditions of the hypersonic winds themselves, HD 189733 exhibits another atmospheric nightmare called wind shear. And this shear is so extreme that it would make the worst turbulence on Earth seem like a gentle breeze. Wind shear is defined as a change in wind speed or direction over a relatively short distance, and it's responsible for some of the most dangerous flying conditions that aircraft can encounter on Earth. On our planet, wind shear occurs near thunderstorms, near jet streams, and in various other meteorological conditions. When an aircraft encounters wind shear, it suddenly finds itself in air moving at a different speed or direction than the air it was just flying through. This can cause sudden changes in airspeed and altitude that can be difficult for pilots to control. Wind shear has been responsible for numerous aircraft accidents, particularly during takeoff and landing when planes are flying at lower altitudes and speeds where they have less margin for error. Modern aircraft have wind shear detection systems, and pilots are trained to recognize and respond to shear conditions. The most extreme wind shear on Earth might involve a change of 50 to 100 miles per hour over a distance of a few miles, enough to create serious danger for aircraft. On HD 189733b, wind shear operates on an entirely different scale. The planet has both vertical and horizontal wind shear that involves changes of thousands of miles per hour over relatively short distances. Vertical wind shear occurs as you change altitude in the atmosphere. At higher altitudes where the pressure is lower, winds can move at the full 5,400 mile per hour velocity of the equatorial jet, but descend into the thicker, denser atmosphere, and the winds slow somewhat due to increased friction and pressure. The transition between these layers creates vertical shear that would subject any object to forces that would tear it apart. Imagine a spacecraft attempting to descend through these layers. As it drops from the high altitude jet into slower-moving air below, it would be subjected to forces trying to rip it in different directions, as different parts of the craft encountered different wind speeds. Horizontal wind shear is equally extreme. The boundary between the fast-moving equatorial jet and slower-moving air at higher latitudes creates shear zones of incredible turbulence. The terminator zone between day and night also exhibits extreme shear as winds change direction and speed in response to the temperature gradient. Objects crossing these boundaries would be subjected to sudden changes in wind speed and direction that would create forces far beyond anything our materials could withstand. Evidence for this extreme wind shear comes from analysis of how light from HD 189733 changes during observations. When astronomers observe the planet, they can detect subtle variations in its brightness and spectrum that result from atmospheric dynamics. Turbulence in the atmosphere creates regions of different temperature and density that scatter light differently. By analyzing these variations, scientists can infer the presence of extreme turbulence and shear in the atmosphere. The data shows continuous variability, consistent with atmospheric conditions that are never calm, never stable, always in a state of violent chaos. This turbulence would make navigation through the atmosphere utterly impossible. On Earth, aircraft can avoid the worst turbulence by changing altitude or course. On HD 189733b, there is no altitude and no course that would provide calmer conditions. The entire atmosphere is turbulent. The entire planet is wrapped in winds that would destroy anything attempting to enter them. This is not a world we could explore with atmospheric probes the way we've explored Venus or Titan. The conditions are simply too extreme for any technology we possess or can currently envision. In 2008, a team of astronomers conducted a detailed spectroscopic analysis of HD 189733 that would reveal one of the most bizarre and terrifying weather phenomena ever discovered on any planet. Using advanced instruments on ground-based telescopes, they carefully analyzed the light passing through the planet's atmosphere during transits, looking for the characteristic absorption signatures of different chemical compounds. What they found initially puzzled them. The spectral signature showed absorption features consistent with silicate particles suspended in the atmosphere. Silicates are the primary building blocks of rocky planets like Earth. They're the minerals that make up most of our planet's crust. The sand on our beaches, the rocks in our mountains, the dust beneath our feet. On Earth, silicates exist in solid form, locked in geological structures that have remained stable for billions of years. Silicon dioxide, also known as quartz, is one of the most common silicate minerals. When purified and melted, silicon dioxide becomes glass, the transparent material in our windows and bottles. Other silicate minerals include compounds of silicon, oxygen, and various metals like magnesium, iron, and aluminum. These are the materials that form the solid, rocky worlds we're familiar with. But on HD 189733b, these materials that we consider solid and stable are behaving in ways that seem almost impossible. The key to understanding this lies in the extreme temperatures on the planet's day side. At 1800 degrees Fahrenheit, temperatures are high enough to vaporize many silicate compounds. The rocky material that must have existed during the planet's formation, perhaps in the form of a solid core, or perhaps as debris that was never incorporated into a core, has been heated to the point where it transitions from solid to gas. Silicon and oxygen atoms break free from their crystalline structures and exist as individual atoms or small molecules floating in the atmosphere. Magnesium, iron, and other metals that would normally be locked in silicate minerals also vaporize, creating a complex atmospheric chemistry dominated by materials that we think of as rocks and dirt on Earth. The process works like this. Any solid particles or larger rocky bodies in the upper atmosphere are subjected to intense stellar radiation. The energy from this radiation breaks molecular bonds, heating the material until it vaporizes. The resulting gas mixes with the hydrogen and helium that make up the bulk of the planet's atmosphere, creating a soup of elements and simple compounds. This material gets caught up in the powerful atmospheric winds and is carried around the planet. As confirmation of this silicate discovery, multiple independent research teams conducted follow-up studies using different instruments and different analysis techniques. Some scientists initially wondered if the blue color might have alternative explanations. Could there be some exotic organic compound producing the color? Could there be unusual scattering from hydrogen and helium molecules under these extreme conditions? But each new study confirmed the original finding. The spectral signatures matched silicate particles. The temperature profile was consistent with silicate condensation. The blue color was produced by light scattering from particles of the right size and composition to be silicate crystals. By 2013, the scientific consensus was clear. HD 189733b has an atmosphere containing significant quantities of vaporized rock. The true horror of HD 189733b's glass weather becomes apparent when we examine what happens as this vaporized silicate material is carried by the hypersonic winds from the day side to the night side. As the gas moves away from the intense heat of the subsolar point and into the cooler regions approaching the night side, the temperature drops below the condensation point for silicate compounds. When water vapor in Earth's atmosphere cools, it condenses into liquid droplets that form clouds and eventually fall as rain. The same basic phase transition process occurs on HD 189733b, except the material condensing is not water but silicate minerals. Silicon and oxygen atoms combine to form silicon dioxide molecules. These molecules cluster together, forming tiny solid particles of what is essentially glass. Other elements like magnesium and iron combine with silicon and oxygen to form more complex silicate minerals. These particles nucleate and grow, similar to how snowflakes form in Earth's atmosphere, except here the resulting crystals are made of materials we would recognize as tiny grains of sand or microscopic shards of glass. The size of these particles varies depending on the specific conditions where they form. Some particles might be just a few microns across, smaller than a human blood cell, essentially dust-sized specks of glass. Others might grow to be tens or even hundreds of microns across, approaching the size of fine sand grains. Under the right conditions, particles might reach sizes of a millimeter or more. Genuine glass pebbles suspended in the atmosphere. These particles form clouds, vast regions of the atmosphere filled with condensed silicate material. But these are not the white, fluffy clouds we see on Earth, composed of water droplets or ice crystals that are mostly empty space. These are dense clouds of glass and rock particles, opaque to visible light, creating regions of the atmosphere that would appear as dark, ominous masses if you could somehow observe them. Once formed, these glass particles don't simply fall gently to lower altitudes the way rain falls on Earth. They maintain the momentum of the wind that's carrying them. Remember, these winds are moving at 5,400 miles per hour. The particles are entrained in this flow, carried along at the same incredible velocity as the surrounding gas. The result is horizontal rain, glass particles screaming sideways through the atmosphere at hypersonic speeds. On Earth, rain falls downward due to gravity. The terminal velocity of raindrops, the maximum speed they reach as air resistance balances gravitational acceleration, is typically around 20 miles per hour. Hailstones can fall faster, perhaps reaching speeds of 100 miles per hour in severe thunderstorms. But even the most extreme hailstorm produces particles that are falling primarily downward under the influence of gravity. On HD 189733b, gravity is utterly overwhelmed by the wind. The particles are being carried horizontally at speeds more than 50 times greater than the fastest falling hail on Earth. This creates a never-ending cycle of remarkable violence. On the day side, silicate material exists as vapor, heated by stellar radiation and mixed throughout the atmosphere. This vapor is caught up in the powerful equatorial jet and carried toward the night side at 5,400 miles per hour. As it enters cooler regions, the vapor condenses into solid particles, forming clouds of glass. These clouds continue to be carried by the wind, the particles suspended in the flow. some particles might grow larger as more vapor condenses on them. Others might collide and stick together, forming aggregates. But the wind never stops, never slows, continuously carrying this material around the planet. Eventually, the wind carries these particles back toward the day side. As they approach the intense heat, the particles begin to heat up. Eventually, they reach temperatures where they vaporize again, turning back into gas and completing the cycle. This process has been ongoing for billions of years and will continue for billions more. It's a perpetual storm of vaporization and condensation, creating clouds of glass that race through the atmosphere at speeds that make them more like bullets than raindrops. To truly understand what this glass rain would be like if you could somehow be exposed to it, imagine standing in the path of this sideways storm. The particles would not be falling from above like rain. They would be coming at you horizontally, screaming through the atmosphere at 5,400 miles per hour. At this velocity, the orientation of the particle's motion relative to gravity is irrelevant. Terminal velocity, the concept that limits how fast raindrops can fall on Earth, is meaningless here. The particles are being driven by wind forces that are many orders of magnitude stronger than gravitational forces. Picture a solid wall of glass particles moving past any fixed point in the atmosphere at hypersonic velocity. The density of particles in the clouds might be similar to a thick fog or a heavy rainstorm on Earth, meaning there could be thousands or millions of particles per cubic meter of atmosphere. Each particle, no matter how small, carries enormous kinetic energy due to its incredible velocity. Kinetic energy is calculated as 1/2 times mass times velocity squared. The velocity term is squared, which means that doubling the velocity quadruples the kinetic energy. A particle moving at 5,400 miles per hour has an enormous amount of kinetic energy, even if it's tiny. Consider a glass particle just 1 millimeter across, about the size of a grain of sand. Such a particle might have a mass of a few milligrams. On Earth, if this particle were falling as hail at 100 miles per hour, it would sting when it hit your skin but wouldn't cause serious injury. But at 5,400 miles per hour, this same particle carries as much kinetic energy as a high-velocity bullet. When it impacts a surface, it delivers a catastrophic amount of energy in a microscopic impact area. Even particles much smaller than this, dust-sized specks of glass just a few microns across, carry enough kinetic energy at these velocities to cause damage on impact. A single particle might not seem like much, but we're not talking about a single particle. We're talking about countless millions of particles in every cubic meter of these clouds, all moving at the same hypersonic velocity. Comparisons to Earth's weather help illustrate just how extreme this is, but they all fall short of capturing the true violence. The worst hailstorms on Earth can produce hailstones the size of baseballs, or even larger, falling at speeds around 100 miles per hour. These storms can shatter car windshields, damage roofs, destroy crops, and occasionally injure or kill people and animals caught in the open. But a hailstorm is a temporary event that lasts for minutes to perhaps an hour, and the hail is falling relatively slowly under gravity. On HD 189733b, the glass rain is permanent, never-ending, always present in the atmosphere. There are no calm periods, no breaks in the storm, no shelter from the perpetual bombardment. And the particles are moving 50 times faster than the worst hail on Earth, carrying thousands of times more kinetic energy. This isn't weather in the sense we understand it. This is a permanent state of atmospheric violence that has no parallel anywhere in our experience. Industrial sandblasting is a process used to clean, etch, or shape hard materials, including metals and stone. The process works by propelling abrasive particles at high velocity against a surface. The kinetic energy of the particles erodes the target material, gradually wearing it away. Industrial sandblasting equipment typically propels particles at speeds between 100 and 300 miles per hour, fast enough to cut through rust, paint, and even solid metal given enough time. Workers operating sandblasting equipment must wear heavy protective gear, including thick gloves, reinforced suits, and helmets with face shields, because exposure to the particle stream can cause serious injuries. The abrasive particles can cut through skin and flesh in seconds. Even brief exposure can cause lacerations and embedded particle injuries. The particle velocities used in sandblasting represent the optimum compromise between erosion effectiveness and equipment limitations. Higher velocities would erode materials faster, but the engineering challenges of accelerating particles to higher speeds make it impractical for most industrial applications. Now, consider HD 189733b, where nature has created a sandblasting environment that operates at velocities 15 to 50 times greater than industrial equipment. The glass particles on this planet are moving at 5,400 miles per hour, carrying kinetic energies that make industrial sandblasting look gentle. What would this do to any exposed surface? The answer is molecular level ablation, the complete destruction of material on an atomic scale. When a hypersonic glass particle impacts a surface, several things happen simultaneously. The kinetic energy of the particle must go somewhere. Some of it goes into deforming or shattering the particle itself, but much of it is transferred to the target material. This energy transfer happens over an incredibly short time span, perhaps a few nanoseconds, which means the power involved is enormous. Power is energy divided by time, and when you deliver a lot of energy in a very short time, you generate extreme power. The impact creates a shock wave in the target material that propagates through its structure. This shock wave can shatter molecular bonds, literally ripping apart the crystalline structure of metals or ceramics. The impact also generates intense heat. The kinetic energy converts to thermal energy, and because the energy is deposited in such a small volume, temperatures at the impact point can exceed thousands of degrees. This is enough to vaporize most materials. The surface material doesn't just wear away gradually as it would in industrial sandblasting. It vaporizes, turning from solid to gas in an instant. Each impact removes a microscopic crater of material. But remember that we're not talking about one impact per second, or even one impact per millisecond. In the dense clouds of glass particles, a square centimeter of surface might be hit by thousands or millions of particles per second. The cumulative effect would be the instantaneous erosion of any exposed material. Metals would be abraded away in seconds. Ceramics would disintegrate. Even advanced materials designed to withstand extreme conditions would fail almost immediately. Consider what would happen to various materials if exposed to this glass rain. Aluminum, commonly used in spacecraft construction, would be eroded away in a fraction of a second. Steel, much harder and more durable than aluminum, might last slightly longer but would still be destroyed almost instantly. Titanium, prized for its strength and heat resistance, would fare no better. The hypersonic impacts would overwhelm any material strength advantage. Carbon fiber composites, used in modern aerospace applications for their high strength-to-weight ratio, would be shredded as the glass particles cut through the resin matrix and broke apart the carbon fibers. Even diamond, the hardest naturally occurring material on Earth, would be eroded away in seconds. Diamond's hardness comes from the strong covalent bonds between carbon atoms in its crystal structure. But the shock waves from hypersonic impacts can break these bonds, and the intense heat generated can convert diamond to graphite or even vaporize the carbon entirely. There is simply no material that we know of, natural or engineered, that could survive exposure to this environment for more than a few seconds. The glass rain of HD 189733b represents an erosion mechanism more powerful than anything we can create artificially and more destructive than any natural process on Earth. Our understanding of HD 189733b's glass weather comes from decades of careful observation using the most sophisticated astronomical instruments ever built. A particularly revealing observation occurred in 2013 when the Hubble Space Telescope observed the planet during a stellar flare, a sudden burst of energy from the parent star. This observation provided crucial insights into the dynamics of the planet's atmosphere. During the flare, the star's output of high-energy radiation spiked dramatically, increasing the heating of the planet's atmosphere. Hubble's spectroscopic instruments detected changes in the atmospheric absorption signatures, revealing how the atmosphere responded to this additional energy input. The observations showed increased ionization of atmospheric gases and changes in the distribution of silicate particles, confirming that the atmosphere is highly dynamic and responsive to changes in stellar radiation. This was direct evidence that the glass clouds we infer from spectroscopy are not static features, but are constantly forming, dissipating, and reforming in response to atmospheric conditions. Scientists cannot directly see the glass clouds on HD 189733b the way we can see clouds on Earth from space. The planet is too far away and too close to its bright star for current telescopes to resolve surface features or atmospheric details visually. Instead, researchers must infer the presence and behavior of these clouds from spectral signatures, the characteristic patterns of light absorption and scattering that result when light passes through the atmosphere. The technique is remarkably sophisticated. When HD 189733 transits in front of its star, some starlight passes through the planet's atmosphere before reaching Earth. Different atmospheric constituents absorb different wavelengths of light. By carefully measuring which wavelengths are absorbed during the transit, astronomers can determine what chemicals are present in the atmosphere and in what quantities. Silicate particles create characteristic absorption features in the spectrum, particularly in certain wavelengths of visible and near-infrared light. The strength of these absorption features tells us how many particles are present. The width and shape of the absorption features provide information about the particle size distribution and the temperature and pressure conditions where the particles exist. But spectroscopy during transits only samples the atmosphere along the limb of the planet, the thin shell of atmosphere visible from Earth's perspective. To build a more complete picture, scientists use additional techniques. Infrared mapping, conducted using space telescopes like Spitzer, measures the thermal emission from the planet at different orbital phases. By observing how the infrared brightness changes as the planet orbits, with different hemispheres visible at different times, astronomers can create temperature maps showing which parts of the planet are hot and which are cooler. These temperature maps reveal patterns consistent with silicate clouds. The regions where silicate vapor should condense based on temperature are the same regions where the planet appears to trap and redistribute heat in complex ways. The correlation between predicted condensation, regions, and observed thermal patterns provides strong evidence that the glass clouds are real and are affecting the planet's heat distribution. Computer models of HD 189733b's atmosphere attempt to simulate the complex interplay of stellar heating, atmospheric circulation, and silicate chemistry. These models start with the known properties of the planet, including its size, mass, orbital distance, and the intensity of radiation it receives from its star. They then simulate how the atmosphere should behave, calculating wind patterns, temperature distributions, and chemical reactions. When the models include silicate vaporization and condensation, they reproduce the observed properties of the planet remarkably well. The predicted locations of glass clouds match the inferred locations from observations. The predicted heat distribution matches the measured temperature maps. This agreement between theory and observation gives scientists confidence that the models are capturing the essential physics of this bizarre world. Research continues as new instruments come online and existing telescopes continue to observe this remarkable planet, each observation adding another piece to our understanding of the glass rain nightmare that defines HD 18973b. HD 18973 is not alone in the gallery of cosmic nightmares. As our exoplanet surveys have expanded and our instruments have grown more sensitive, we have discovered dozens of worlds that challenge our understanding of what planets can be. Each of these nightmare worlds reveals a different aspect of the extreme conditions that can exist on alien planets, and each one makes us grateful that Earth is so remarkably gentle by comparison. Among all the hellish exoplanets ever discovered, one stands above the rest in terms of pure, overwhelming heat. Kelt 9b holds the record as the hottest exoplanet ever detected, with dayside temperatures reaching approximately 7,800 degrees Fahrenheit, or 4,300 degrees Celsius. To put this in perspective, this is hotter than the surface of most stars. Our own Sun has a surface temperature of about 10,000 degrees Fahrenheit, making Kelt 9b more than 3/4 as hot as the Sun's surface. At these temperatures, molecules simply cannot exist. Chemical bonds are ripped apart by the intense thermal energy. The atmosphere of Kelt 9b is composed not of molecules but of individual atoms, a plasma of ionized particles. This planet orbits a massive blue star, much larger and hotter than our Sun. Blue stars are the most massive and luminous stars in the universe, burning through their nuclear fuel at prodigious rates and emitting enormous amounts of energy, particularly in the ultraviolet portion of the spectrum. Kelt 9b orbits this stellar furnace at a distance even closer than HD 189733b orbits its star, resulting in the most intense radiation bombardment of any known planet. The atmospheric composition of Kelt 9b is unlike anything we've encountered elsewhere. Spectroscopic observations have detected vaporized iron, titanium, sodium, magnesium, and other metals in the atmosphere. On Earth, these are solid metals that we mine from the ground and forge into tools and structures. On Kelt 9b, they exist as gaseous atoms floating in the atmosphere, heated to the point where even the most refractory materials cannot condense. But even this planet has a night side, and even here there is a temperature differential between the side facing the star and the side in darkness. The night side is relatively cooler, perhaps dropping to a mere 4,000 degrees Fahrenheit. At these lower temperatures, some of the vaporized metals can condense. Iron vapor, which cannot exist in liquid or solid form on the day side, condenses into liquid droplets on the night side. The result is rain made of molten metal, droplets of liquid iron falling through the atmosphere like an infernal parody of a rainstorm. Titanium, with its higher boiling point, might also condense under the right conditions, creating a mixed metal precipitation unlike anything imaginable on Earth. Kelt 9b was discovered in 2018 using transit observations, and follow-up studies have revealed that the planet is slowly being destroyed by its star. The intense ultraviolet radiation is stripping away the atmosphere at an enormous rate. Atoms in the upper atmosphere are heated to such high velocities that they achieve escape velocity and are lost to space forever. The planet is surrounded by a vast cloud of escaping gas, creating a comet-like tail of atmospheric material being blown away by stellar radiation pressure. Over hundreds of millions of years, Kelt 9b may lose a significant fraction of its mass, potentially being reduced to a bare core or even being completely destroyed. This is planetary death in real time, a world being slowly vaporized by its own star. Another world of metal rain presents a different variation on this nightmare theme. WASP-76b, discovered through transit observations and studied intensively since 2020, exhibits a weather pattern so bizarre that it seemed almost unbelievable when first detected. This planet orbits its star at a distance that creates dayside temperatures of approximately 4,400 degrees Fahrenheit, hot enough to vaporize iron, but not quite as extreme as Kelt 9b. The key to understanding WASP-76b lies in its dramatic day-night temperature contrast and the resulting atmospheric circulation. On the day side, iron exists entirely in vapor form. The metal atoms are mixed throughout the atmosphere, carried upward by convection, and dispersed by atmospheric turbulence. But WASP-76b, like HD 189733b, is tidally locked, which means it has powerful winds that transport atmospheric material from the hot day side to the cooler night side. As iron vapor is carried toward the night side by these winds, it enters regions where the temperature drops below iron's condensation point of approximately 3,000 degrees Fahrenheit. At this point, the iron atoms begin to combine, forming first small clusters and then larger droplets of liquid iron. These droplets are heavy, much denser than the surrounding hydrogen and helium atmosphere, so unlike the silicate particles on HD 189733b that are carried horizontally by the wind, iron droplets on WASP-76b actually do fall, pulled downward by gravity to descend into the deeper, hotter layers of the atmosphere, where they vaporize again. The result is a cycle of iron precipitation. Vapor on the day side is carried to the night side by winds, condenses into liquid droplets that fall as rain, and then vaporizes again in the deeper atmosphere, only to be carried back toward the day side by the return circulation at lower altitudes. In 2020, astronomers using the Very Large Telescope in Chile made a remarkable discovery about WASP-76b that confirmed this iron cycle and revealed even more detail about the planet's atmospheric dynamics. Using extremely high-resolution spectroscopy, they detected iron vapor in the planet's atmosphere, but only on one side of the terminator zone. Specifically, they found iron vapor on the evening terminator, the boundary where the planet is rotating from day into night. But they did not detect iron vapor on the morning terminator, where the planet rotates from night into day. This asymmetry is exactly what you would expect if iron is being carried from day side to night side by winds, condensing on the night side, and then raining out of the observable upper atmosphere. On the evening side, vapor-rich air from the day side is just arriving, so iron vapor is present. On the morning side, the air has already had time to cool, and the iron has already condensed and rained out, so no vapor is detected. This observation provided direct confirmation of the iron rain theory, and demonstrated that we can actually observe these exotic weather patterns in action, watching metals cycle between gas and liquid phases in alien atmospheres. Moving beyond metal rain, we encounter worlds with even more exotic atmospheric chemistry. Haiti P7b, a hot Jupiter orbiting a star approximately 1,000 light-years away, features clouds made of corundum, the mineral form of aluminum oxide. On Earth, pure corundum is transparent and colorless, but when it contains trace amounts of certain impurities, it becomes the gemstones we know as rubies and sapphires. Chromium impurities create the red color of rubies, while iron and titanium impurities create the blue color of sapphires. On Haiti P7b, the clouds floating in the atmosphere are composed of microscopic crystals of this same material, essentially clouds of tiny rubies and sapphires drifting through alien skies. The temperatures on Haiti P7b reach approximately 4,000 degrees Fahrenheit, hot enough that aluminum oxide can exist in vapor form in the hottest regions of the atmosphere. As this vapor is transported to cooler regions by atmospheric winds, it condenses into solid crystals of corundum. The formation of these crystals follows similar principles to how snow crystals form in Earth's atmosphere, with vapor molecules attaching to growing crystal structures, but the resulting crystals are chemically and physically very different from water ice. Corundum is one of the hardest naturally occurring minerals, second only to diamond on the Mohs scale of hardness. The clouds on Haiti P7b are literally made of tiny abrasive gemstones being carried through the atmosphere at high velocities. In 2016, astronomers analyzing data from NASA's Kepler Space Telescope made a fascinating discovery about Haiti P7b. By carefully measuring how the planet's brightness changed over time, they detected variations that indicated changing cloud patterns. The planet would become slightly brighter or dimmer as clouds formed and dissipated, or as wind patterns shifted the cloud distribution. These observations showed that the gemstone clouds are dynamic, constantly changing in response to atmospheric conditions. The wind patterns on Haiti P7b appear to push clouds preferentially toward one side of the planet, creating regions that are cloudier and regions that are clearer. This is similar to how weather patterns on Earth can create regional variations in cloud cover. But here, the clouds are made of materials that would be considered precious gemstones if they existed on our planet. The exotic chemistry that creates these corundum clouds depends on the presence of aluminum and oxygen in the planet's atmosphere in the right proportions. In oxygen-rich atmospheres, aluminum readily combines with oxygen to form aluminum oxide. The high temperatures on Haiti P7b ensure that this material cycles between vapor and solid phases, creating the clouds we observe. This represents yet another example of how familiar materials from Earth's geology can exist in completely alien forms on exoplanets, behaving as atmospheric constituents rather than as rocks and minerals locked in a planet's crust. For a glimpse of truly extreme rocky world conditions, we must examine CoRo T7b. Discovered in 2009 as the first confirmed rocky super-Earth beyond our solar system. This planet represents a different category of nightmare world. Not a gas giant like the others we've discussed, but a rocky planet with perhaps twice Earth's diameter and several times Earth's mass. What makes CoRo T7b horrifying is its proximity to its star. The planet orbits at a distance of only 1.6 million miles, even closer than Kelt 9b, completing a full orbit in just 20 hours. This is not a typo. A year on Coro T7b lasts less than 1 Earth day. At this distance, the dayside surface reaches temperatures of approximately 3,600 degrees Fahrenheit, hot enough to melt rock, to vaporize most minerals, and to create an atmosphere composed of materials that we think of as the solid substance of planets. On Earth, our atmosphere is made of gases that are volatile under our conditions: nitrogen, oxygen, water vapor, carbon dioxide. These are materials that naturally exist as gases at Earth's surface temperatures and pressures. On Coro T7b, the atmosphere is made of vaporized rock. Silicates, sodium, potassium, and other elements that make up rocky planetary crusts are heated to the point where they turn to gas and form an atmosphere surrounding the planet. This atmosphere is unlike anything we can easily imagine. Think of it as the steam that would result if you could heat rock to boiling, except maintained continuously over the entire dayside of the planet. As this rock vapor is transported by winds toward the night side, where temperatures are lower though still exceeding 1,000 degrees, the vapor cools and condenses. But it doesn't condense into solid particles like the silicate clouds on HD Wait T973. On Coro T7b, the condensation produces liquid rock, molten lava droplets that fall as rain on the night side. This is a planet where it literally rains lava, where droplets of melted stone fall through the atmosphere and splash onto a surface that is itself partially molten. The geology of Coro T7b must be extraordinarily dynamic. The day side might be entirely molten, a global magma ocean that never has a chance to cool and solidify. The night side might have a thin, solid crust that is constantly being eroded by the lava rain and constantly being rebuilt as the rain cools and solidifies. Tidal locking ensures that the same hemisphere always faces the star, creating a permanent geography of heat, a day side forever molten and a night side forever being pelted with liquid rock. The composition of Coro T7b is thought to be similar to Earth's rocky planets, primarily silicates and metals, but its surface conditions are more extreme than the most violent volcanic events in Earth's history. The Deccan Traps in India, massive lava flows that occurred 66 million years ago, and the Siberian Traps, even larger lava flows 252 million years ago, represent the most voluminically productive volcanic events on Earth. But these were temporary events lasting perhaps hundreds of thousands of years. On Coro T7b, the entire day side is a permanent lava ocean, and the night side experiences continuous lava rainfall, a state of geological violence that has persisted for billions of years and will continue until the planet is eventually destroyed by tidal forces or consumed by its star. Perhaps the strangest world in terms of composition is 55 Cancri A, a super-Earth orbiting a sun-like star just 40 light-years away. What makes this planet remarkable is not primarily its temperature or weather, though it is certainly hot with surface temperatures reaching approximately 4,900 degrees Fahrenheit, but rather its possible internal composition. In 2012, a team of astronomers proposed a radical idea. Based on the planet's mass, radius, and the known composition of its parent star, they suggested that 55 Cancri E might be extraordinarily rich in carbon. Most rocky planets, including Earth, are dominated by silicates, minerals made primarily of silicon and oxygen with various metals. But if a planet forms in a region of the protoplanetary disk that has more carbon than oxygen, the chemistry changes dramatically. Instead of forming silicates, carbon combines with metals and with itself to form carbides and pure carbon structures. The proposal suggested that 55 Cancri E might have an interior composed largely of diamond and graphite, rather than the silicate rocks we're familiar with. Diamond is a form of pure carbon where each carbon atom is bonded to 4 other carbon atoms in an extremely strong three-dimensional lattice. This structure makes diamond the hardest naturally occurring material and gives it unique thermal and optical properties. Graphite is another form of pure carbon, where atoms are arranged in sheets that can slide past each other, making graphite soft and slippery despite being made of the same atoms as diamond. Under the extreme pressures and temperatures inside a massive super-Earth, carbon could exist in both these forms and potentially in even more exotic high-pressure phases. The surface of 55 Cancri A, if this hypothesis is correct, might be covered with a layer of graphite or diamond, perhaps with pools of liquid carbon or even oceans of molten carbon compounds. The atmosphere would be dominated by carbon monoxide and other carbon-bearing molecules rather than the oxygen and nitrogen we're familiar with. This would create a completely alien geochemical environment, a world where the fundamental chemistry of rocks and minerals is based on carbon rather than silicon. The diamond planet hypothesis remains controversial. Subsequent observations and analyses have suggested that 55 Cancri E might have more oxygen in its composition than initially thought, which would reduce the amount of free carbon available to form diamond. But even if the planet is not as carbon-rich as the original hypothesis suggested, it likely has a very different composition than Earth-like rocky planets, with significantly more carbon and significantly less oxygen in its makeup. This raises fascinating questions about planetary diversity. We've tended to assume that rocky planets will be broadly similar to Earth, Mars, Venus, and Mercury, all made primarily of silicates and metals. But the universe may contain entire classes of rocky planets with fundamentally different chemistries: carbon planets, water planets, iron planets, each with its own unique geology and geochemistry. The exotic conditions on 55 Cancri A, whether or not it's truly a diamond world, remind us that planets can be far stranger than our limited experience in one solar system has prepared us for. These nightmare worlds, from the glass rain of HD 189733 to the metal rain of Kelt 9b, and WASP 76b, from the gemstone clouds of HAT P7b to the lava rain of Coro T7b, and to the possible diamond interior of 55 Cancri E, represent just a small sample of the extreme conditions that exist on planets throughout the galaxy, each one a testament to the diversity and hostility of alien worlds.